Okay, well, good morning, good afternoon, good evening. Thank you for joining us today. This webinar will be specifically on flue gas analyzers for safe combustion of high hydrogen fuels. And in our presentation today, we will talk about the role of flue gas analyzers in order to drive for safer combustion of high hydrogen fuels. In our agenda today, we'll talk about the trends driving to decarbonization. We'll talk about the use of hydrogen in fuels and really evaluate those risks and implications of using hydrogen as a feedstock in comparison versus methane. We will also talk about the three critical roles of flue gas analysis and how it pertains to combustion and safe combustion. We'll also get a little bit deeper and talk about the detector types that can detect hydrogen and how they can be used for detecting unsafe conditions. Finally, we'll conclude with just some of the key flue gas measurements to consider for combustion safety and for process control as you move to a high hydrogen fuel. So as I mentioned, please feel free to post any questions in the chat during this presentation. There will be time at the end for questions as well, but thank you for joining us today. Now let's start it off with trends in decarbonization. Now the first thing I want to point out is that there is a global movement towards decarbonization. Governments have made commitments across the world. Companies have made commitments across the world in evaluating their role in climate control and thinking about how they can reduce greenhouse emissions and specifically carbon dioxide. Now, as we confront these global climate commitments, we also evaluate that there are many industries that require combustion for heat and for power. And there's a lot of very hard industries to decarbonize, which include steel and cement and chemicals, which require and will continue to require combustion as a primary sort of heating. But there's also the mobility considerations. So for ships and air traffic and trucks, that will continue to need some amount of combustion for long hauls and for industrial uses. So as we overlay that with different decarbonization techniques, there are a few that come up pretty often. And one that comes to mind for large-scale decarbonization is that of carbon capture. Now, carbon capture is after the combustion process. You can remove the carbon emissions. There's certain different ways to do prior, pre-combustion carbon capture, but ways of thinking about removing carbon emissions before or after or during the combustion process. So that's one large-scale decarbonization path to pursue. There's also electrification, which certainly has its place in certain applications, especially smaller applications, and that would be to generate heat in place of combustion. Although that has its very specific, place in the decarbonization effort. And the next thing to really consider is also that of hydrogen fuels to generate heat without carbon emissions. And so as we look to combustion in the future, combustion processes will continue to remain important as we look towards the future of decarbonization and towards industry. So let's talk about those three different decarbonization paths. Let's talk about carbon capture, let's talk about electrification, and let's talk about hydrogen as a fuel. So if you look at the first one, carbon capture again is removing CO2 directly from the combustion process, before, during, or after the combustion process. And if you think about it, it's very economical. It's much more economical in cases where the emission sources are very centralized. So if you have one duct that's providing that's creating a lot of emissions, it's helpful to think that you could have some downstream equipment that could scrub out the carbon that you're generating. The challenge is, however, when you think about a number of combustion applications where there are many stacks or many small dispersed point sources of flue gas and emissions, then it becomes a bigger project for how do you duct all of these small dispersed sources to really capture to take all the flue gas into one specific place. So that can become a bigger challenge or require much more upfront capital for many dispersed sources. So carbon capture really has its place around centralized emission sources. Okay, well, what about electrification? Well, electrification is interesting in that it can certainly generate heat in place of combustion. So it certainly does lend itself very well to like new facilities, greenfield plants, and also low temperature applications, where there's not a big heat duty requirement, where there's not a big change of very high temperatures required. But the challenge again becomes, what do you do with an existing facility, an existing plant, and do you replace all of that with electrification? Do you partially replace it with electrification? And what's that return on investment? So how do you do that economics for existing plants? And then how do you face the real challenge of dependence on external power sources? Because anything with electricity will require some type of power source. And certainly green hydrogen and electrification and solar panels has its place too. But it's also, is that upfront power source sufficient for the electrified pieces of equipment downstream? So electrification is a balancing act as well for where does it have its best place. Now, if you think about something like a hydrogen fuel, which generates heat without carbon emissions, that can be versatile by using as a fuel in a combustion process that are both centralized sources of fired equipment, as well as dispersed sources, like many fired heaters, for example. So hydrogen as a fuel could be used in a boiler, could be used in a fired heater, could be used in a thermal oxidizer, and it can be used with great variability, with minor changes to the upfront equipment. So that's one thing. There's also minimal impact at the combustion source. Again, minimal changes required to repurpose the burner or piping for hydrogen. It still has to be evaluated, but it's something that can be done ahead of time with generally minimal impact on the combustion source. The other thing is that for an existing facility, uh, plot space and land are a premium. And by repurposing a combustion process to the use of hydrogen to reduce emissions, you also lend yourself to not having to expand very much of the plant, not having to build on top of what you already have. So that also has an advantage as well, followed by the fact that hydrogen has been generated as a byproduct fuel in many other industries, and it's been used very often as part of refinery fuel gas, as one example where you see hydrogen being produced from the process upstream, and it can be used as its own fuel source. So a number of these evaluations came from the technology assessment of hydrogen firing of fired process heaters, and ultimately, what it comes down to it is that hydrogen as a fuel offers the most versatility for existing combustion processes. Okay, so that just provides some context. Let's next talk about some of the actual properties of hydrogen. How do we even think about that in comparison to methane as we move towards a different fuel source? So as we think about those physical properties, the first thing we can talk about is that of molecular weight. Okay, so if you look at it just first glance, you'll notice that hydrogen is much smaller compared to methane, uh, 8 times the mass, if you will, per mole. Also, physically, it's lighter. It's eight times less dense compared to methane. So you also have to think about that relative density. That density causes it to, to, to be lighter in the atmosphere, and also it causes it to be have a faster molecules. Hydrogen molecules are 3 times faster compared to methane. So we have a lighter, faster molecule in comparison with methane. And then finally, its flammability is on a much wider range as well. So flammability limits really 4% to 75% by volume for hydrogen compared to the narrow window of methane. So that wider range of flammability is something that absolutely be mindful of for some type of fuel-rich condition. So the major first glance thing to consider is that hydrogen is lighter. It's 8 times lighter, it's 3 times faster, and it's more flammable versus methane. Okay, so that's really something to consider up front. Now, the next thing to think about is the combustion properties. Okay, so it's lighter, it's faster, it's more flammable. Well, if it's more flammable, how does that flammability relate to combustion? So if you look at the gross heating value on a volumetric basis, uh, you need more hydrogen by volume compared to methane to meet the same heat release. So that's roughly 3 times the volume needed to get the same heat release. However, if you're measuring on a mass flow basis, it's just the opposite. You need less mass flow of hydrogen as a fuel for the same heat value. So hydrogen as a fuel requires about a third less the mass flow versus methane. Okay. So being mindful of mass flow versus volumetric flow really matters when it comes to comparing the properties of using hydrogen as a fuel compared to methane. Something else to consider is that of flame speed. Hydrogen flames are 10 times faster compared to methane. And that is important to think about because hydrogen has shown a lot of issues of potential flashback with premix burners, for example. So flashback is something to think about because you don't want the flame to walk backwards so much that it causes a flashback scenario. Something else to consider is also the heat. Hydrogen flames are hotter, slightly, but they're hotter compared to methane. And they are also react at a lower temperature. Again, slightly in comparison to methane, but it still reacts at a lower temperature compared to methane. And lastly, from a combustion property standpoint, less energy is needed, 10 times less energy is needed compared to methane. So when you look at that from this perspective, hydrogen flames are 10 times faster, they burn hotter, and they really vary depending on the heating values versus volumetric versus mass flow basis. Now, some other things that I want to point out is that it's not just about the combustion properties, not just about the physical properties. There are other implications to consider as well. Primarily, that if you were to get the same heat release and compare the hydrogen heat release versus the methane heat release, if you adjust them for the same heat release, you might be able to tell, but you need 20% less air when combusting hydrogen versus a methane fuel. So that's important to consider because if you were going at one combustion airflow rate with methane, you may need to adjust it down for hydrogen further, but you would need to proactively adjust higher as you step back from hydrogen to methane. You would not want to use 1.6 in the 20% less. You wouldn't want to use 20% less air for methane. That would cause an unsafe condition. That would cause a potentially fuel-rich condition. So being mindful of the hydrogen and how does that need, it needs less air compared to hydrogen. One other thing to think about is because the hydrogen molecules are faster and they have a faster flame and a shorter flame, that shorter flame has more opportunities to create a hot spot within the flame. And that hot spot within the flame, even with a low NOx burner, has a potential to create more NOx. So you want to balance and be mindful of using hydrogen to reduce carbon dioxide, but the potential risk of having more NOx generated. So it's a balancing act as well on the air side and also on the emission side. So that's just the upfront properties and comparisons between methane and hydrogen. With that in mind, what kind of risks can we anticipate with this? So there are a number of potential risks to consider with high hydrogen fuels. The first risk that comes to mind, especially throughout industry, is thinking about the risk of flashback, especially that in premix burners. It's certainly a common experience to flashback burners because of that faster flame speed. So anticipating that, also being mindful if you have a premix burner to monitor for this type of unsafe condition, this type of flashback risk. Also, there's the risk of thermal NOx production. Again, because you have that shorter flame with faster molecules has a risk of higher NOx. So this is something that you would want to be thoughtful of, especially because a number of permits are written on a ppm basis, and some of them to a dry basis. So you want to be mindful of, if you're going to generate any more NOx and generate more water, how does that impact your permits? So generating thermal NOx is certainly something that is not just it becomes a regulation thing and a compliance thing as well. So being mindful of the amount of extra water you're generating and then also the potential higher NOx that you're generating. Other things to keep in mind is also the risk of hotter tubes, because the flame is shorter on a hydrogen flame. You also want to be mindful of certain geometries in the firebox that may see higher temperatures that could impact metal, that could impact refractory, that could impact the burner. So being mindful, or the radiant tubes as well around the burner. So all these things, it's something to keep in mind, especially as operators move from methane or other fuels to hydrogen fuels. The next thing to consider here is also the risk of overheating near the burner. Just as I said before, metal parts can be exposed to the flame, could have higher operating temperature. So you want to make sure that can dissipate the heat, and evaluate the need if you need to upgrade materials or not. So definitely something to consider and talk to your burner manufacturers as you were to retrofit from a typical design to a design ready for hydrogen. And finally, the last one, which is most applicable to a flue gas analysis scenario, is that of the risk of accumulation of a combustible vapor. What happens if a flame goes out, especially if you have a fired heater which has many burners? What happens if a flame goes out? You have loss of flame. What happens if a burner leaks? So how do you handle any pockets of uncombusted hydrogen? How do you handle this increased reactivity and molecular speed in a loss of flame scenario? So this is where flue gas analysis comes in for added safety. Also thinking about how you can balance the safety margin at the burner. And we'll talk about that in a couple slides from now. But really, flue gas analysis, as we talk about flue gas analyzers for safe combustion of high hydrogen fuels, it's important to think about the risk associated with hydrogen fuels, risk of an unsafe condition of a loss of flame, and how do you increase safety and reduce risks through flue gas analysis. So let's talk about flue gas analysis. Now, if we think about flue gas analysis, we also have to think about combustion. So really, combustion requires oxygen, fuel, and heat. In any case, a combustion scenario is going to generate some amount of incomplete combustion due to poor mixing at the burner, changing loads, and of the fuel concentration, variable fuels going from methane to hydrogen, going hydrogen to some other type of fuel, methanol, and also maybe malfunctioning burners. Maybe there's a fuel tip, a flame tip that was corroded away or needs to be replaced. So I'm going to be using the term combustibles a lot in this presentation moving forward, and something to think about as you look at these two just generic reactions. If you have oxygen with hydrogen or oxygen with methane, is that there's going to be some amount of incomplete combustion. There's going to be some amount of carbon monoxide and hydrogen generated from a methane type fuel. That'll generate combustibles at ppm levels. If there's enough oxygen, it'll proceed to generate carbon dioxide in water. So when I think about critical measurements for combustion, I think about excess oxygen as a set point, combustibles for safety and burner optimization, methane and hydrocarbons to detect flame out and gas leaks, and also sample flow to make sure that the analyzer sample is reflective of the process. And so I'll go into each of these to really make the case for them. But I want you to think about these as relevant measurements, especially when it comes to combustion and flue gas analysis. So let's just do a quick overview of combustion and stoichiometric combustion. If we think about it with the case with methane and oxygen, you get the the maximum heat transfer, the maximum efficiency in the case of stoichiometric conditions, where you have the perfect amount of air, the perfect amount of fuel. And in this particular example, you generate 23,000 BTUs per pound, and all of the methane is converted to carbon dioxide and water. Perfect scenario. Now, in reality, this is not really attainable, and we need some amount of safety margin. So, and that during normal operation, we typically operate a little bit excess air at the burner, a little bit excess oxygen in the flue gas. And in this particular example, if you have an excess of air at the burner, you generate an excess of oxygen in the flue gas and some normal amount of part per million levels of carbon monoxide and hydrogen. And this would be the same if it was hydrogen as a fuel, although it would be part per million levels as well. And in this case, it's 6% roughly less efficient, but it provides enough safety margin to convert all of the fuel to carbon dioxide to water with some amount of leftover oxygen and some low levels of combustibles. Now, an unsafe condition would be if you have too much fuel. Unless your process is designed for reducing, an oxygen deficiency or a fuel-rich condition are both very dangerous. And the reason for that is because the fuel does not get completely combusted or oxidized, and as a result, you have extremely high levels of combustibles. So not only is it an efficiency issue, 35% less efficient, but it's also a risk of it's a safety risk. It's an explosive mixture risk because you have more combustibles flowing out the stack than you do oxygen. And notice in this case that there's no excess of oxygen in the flue gas. So this is an example of a fuel-rich condition, also an unsafe condition, with too much fuel going to the burner. Now, if you were to look at just the normal case, where you have an excess of oxygen in the burner and an excess of oxygen in the flue gas. If you were to look at, say, 3% oxygen in the flue gas, this would directly correlate with about 20% excess air at the burner. And this is using natural gas as an example. I will get to hydrogen in just a second, but for this particular example, there's a correlation, and I did the math to create this slide. There's a direct correlation between the excess oxygen in the flue gas and the excess air at the burner. And this is the same with even like 2%, where if you have 2% excess oxygen in the flue gas, that's roughly a safety margin of about 12% excess air at the burner. So you can consider this vertical axis as the safety margin that you have at the burner. And so if you think about a typical operating range between 2 and 3% excess oxygen in the flue gas, you can think about that as a rough correlation of about 11% to 20% excess air at the burner. Now, if you were to look at this from the perspective of hydrogen, the correlation still stands pretty close. With hydrogen, at 2% hydrogen, roughly, it's about a 12 to 13% safety margin at the burner, and at 3%, it's roughly 22% excess air at the burner. So at very similar ranges, you have a very similar amount of safety margin. And so the importance of that is being mindful that any excess oxygen, again, excess after everything else is combusted, any excess oxygen at the burner is a direct correlation of a safety margin. And this is important because fire heaters that use the oxygen measurement for flow control of the downstream air ensure that there's an excess oxygen measurement to drive the secondary air and ensure that there's an accurate air to fuel ratio at the burner. And that's the same with thermal oxidizers. That excess oxygen measurement can be used to drive downstream dampers or upstream dampers for feedback to ensure that you have the right amount of air in the firebox. Now, that being said, that's the perspective of really flue gas analysis and how it all fits from a operational standpoint. So if we think about the roles of flue gas analysis, we really talked about the first one. The first one is really that when you operate, that excess oxygen measurement provides a direct correlation to the air-to-fuel ratio at the burner, and ensures that you have this accurate safety margin, the sufficient air to provide to the burner as a safety margin. So the first role of flue gas analysis, the first thing to think about when it comes to even excess oxygen measurement, is that you need a set point. You need a safe set point so that you have enough air at the burner, so that you have enough excess oxygen downstream. If we talk next about the role of optimization, we've already talked about the excess oxygen curve. But the one thing I want to add is that as you go further and further out with excess oxygen, you also have increasing amounts of CO2. Because as you have more excess oxygen, you need more fuel to be consumed to heat up all the inerts, the inert being the excess oxygen and the excess nitrogen that passes through of the combustion air. So as you increase excess oxygen, you also increase your CO2 emissions, you increase your NOx emissions, you increase your fuel usage. So there is an efficiency that you lose when you have too much excess oxygen. So we can have one set point right here at 2%, but if we go higher, we have less efficiency. But if we go lower, how low is the right amount of low before you get to an unsafe condition? So an excess oxygen measurement by itself is important for operational set point. But if we start talking about combustibles, that intermediate measurement for combustion, combustibles has a very different curve, a very different response to excess oxygen. With combustibles, as you have increasing amounts of excess oxygen, you have lower and lower and lower and lower levels of combustibles. So that's helpful when you want to reduce your combustibles in a specific application. But the challenge is that if we want to reduce our excess oxygen, because that has an increasing amount of inefficiency, then we have to be mindful that there's this combustibles breakthrough point. If you get too low, that converts this nice linear trajectory of combustibles to an exponential increase. And so if you look at these two measurements together, you can have a better picture to better optimize your process. And so where a typical operating set point might be 2%, you may be able to lower that to 1% excess oxygen to a more optimum control point that doesn't get too close to combustible breakthrough, that gives you some space before combustible breakthrough, but also a lower excess oxygen set point so that you can reduce your emissions and have a better return on investment for your fired equipment. So less fuel usage, less emissions, less permitting penalties, if you will. So like I mentioned, excess oxygen is a set point by itself. When you consider combustibles, that is an added benefit to reducing losses from efficiency. The lower excess air reduces less emissions and also reduces your fuel consumption and also avoids unsafe conditions by using a combustible measurement. Now, one thing I will say is that it's very dependent. Combustion optimization is what we call it, and combustion optimization is very dependent on the fuels that you're using. So in this example, that same curve put a different way for combustibles. Natural gas might have a very low combustibles breakthrough point. Oil might be higher. Coal could be even higher, where you have to be mindful of the smoothness of the curve. So that optimal range varies greatly depending on the fuel that you're using. And so what is the optimal excess oxygen level? That really depends on the process. There's many factors at play with every different process equipment, everything from how tropical you are to how variable the fuels are to the humidity changes to how's the burner doing, how is it fouling, is it plugging, what's the mechanical wear on the combustion system. So there's no fixed value for any of these fuels, and you have to be very mindful of especially varying fuels, of variable fuels and different heating content of your fuel as you switch your fuels. And that makes it more and more important for having a combustible measurement so that you can detect that you're not too close to combustible breakthrough, and also so that you can detect your more optimal excess oxygen set point. So when we think about the flue gas analysis role of optimization, it's important to think about the health of the combustion process, how much combustibles are generated in a specific application, but it also provides this reference point, the secondary reference point, to determine what's the optimal amount of excess air, so that you can reduce your CO2 emissions, so that you can reduce your NOx emissions by ultimately reducing your fuel consumption. And then this last part, the role of safety. When we think about flue gas analysis and safety, we've already talked about combustible breakthrough. Combustibles detectors alert for this combustible breakthrough set point. So this is important, and this is a very important part of combustion optimization, monitoring for these ppm levels of combustibles and alerting for incomplete combustion. Very important for the role of safety. There's also the opportunity to use a hydrocarbon measurement to detect high levels of fuel. So like I mentioned, you could have a fuel leak at the burner, or to create a burner tip that could be releasing too much fuel, or a leaking burner, or leaking fuel valve. There's also the potential issue of having a loss of flame. That could happen from too little air or too much air where it blows out the flame. In either case, you'd want to be alerted of that loss of. You would want to be alerted of that increase in unburned fuel. You want to be alerted of that unsafe condition, this loss of flame, of this leaking fuel, so that you can better equip yourself. And a methane hydrocarbon detector alerts this loss of flame, monitoring for fuel-rich conditions for a normal operation, but also for loss of flame during startup and ignition, where the percent levels may be very high. And even as operators start moving towards hydrogen as a fuel and hydrogen fuels, you also have to be confronted with startup conditions. And in many cases, a lot of startup conditions are going to remain with natural gas because it's more stable, it's relatively slower. So having a hydrocarbons measurement that can detect hydrogen is a big advantage to make sure that startup conditions are safe, and also that you're not doing light off with a very light off with hydrogen, for example, that would be very spark privy and very light and fast and higher flammability limit. So a lot of operators are still using natural gas for startup and ignition, and it'd be important to be mindful of that for when thinking about whether or not to use methane hydrocarbon detector for loss of flame. So with that, if we think about safety and kind of bring it all together, the last role of flue gas analysis is the role of safety, and also being mindful of detecting percent levels of hydrogen and hydrocarbons for fuel leaks and loss of flame. Okay, so I know we've covered a lot already. The next thing I really want to put our attention to is these are the three critical roles of flue gas analysis. Okay, a lot of it hinges on the capabilities and advantages of having a combustible measurement. Well, let's next talk about these catalytic detectors, how they can be used to measure methane, combustibles, and also hydrogen, and how does it all work together. So as we start to think about catalytic detectors, what's unique about them is that they monitor for a range of compounds. A catalytic detector uses a catalyst, and very often these catalysts are not selective to any specific species. Uh, they can be tuned, and I'll get to that in a second. They can be tuned to a very specific window, but they're greatly not they're greatly unspeciated. So with that in mind, we have two different types of catalytic detectors that are in use today. There's the RTT thick film type, and also the catalytic hot wire bead type. And just an example of our RT detector is this right here, where you can see that there's a catalytic element, there's a reference element, and in this case, it uses the RTD. We also have the hot wire detector, where there's two beads. This is just a zoom in of one bead, but there'd be two beads side by side that are put across effectively a weak stone bridge in a number of cases. The unburnt hydrocarbon would be, or the combustibles would oxidize on the surface, and how that oxidation is received changes the resistance on the hot wire beads, and that causes a difference in the voltages or the resistances, excuse me, that ultimately give a measurement. So these are the two different types of catalytic detectors. In both cases, there's two elements. In this case, you can see there's the catalytic element and the reference element. For the catalytic type, there's two elements as well. There's the reference and then the active side by side for the catalytic bead as well. Now, uh, in both cases, these detectors are actively oxidizing the unburnt hydrocarbons and or the combustibles in the process. And oxidation requires oxygen, so these measurements require the available oxygen in the flue gas to oxidize the sample. Now, this is important because this oxidation in the sample provides the measurement. Now, if you get too close to fuel-rich condition, we have fail-safes to go from uh, the measurement to full scale if it gets below a certain oxygen concentration. So we're certainly mindful of too low of oxygen concentrations. If the oxygen concentration gets too low, we ultimately go to a fail-safe condition and go to full-scale combustibles, full-scale methane in any of the packages that we have. But something to be mindful of is that we are oxidizing. So as you get a better up-to-date combustibles measurement, as you get a better up-to-date methane measurement, your excess oxygen will also respond accordingly to the increasing amounts of combustibles and or methane and hydrocarbons. Now, with that in mind, I do want to be mindful of the fact that these are all tuned to a very specific zone of reactivity. And that's a very specific choice of words. These detectors are operated with certain currents, and those currents allow the measurements to be to a very specific window. So between calibration and current, together they create a zone of reactivity. And so that zone of reactivity is for combustibles, it's the zone of reactivity between carbon monoxide and hydrogen. For methane, it's effectively between hydrogen and methane. But in any case, uh, other things are detected or can be detected on a combustible measurement on a methane detector. And so that unspeciation allows for detection of other flammable gases. But like I mentioned, calibration is critical for making sure that the measurement reading is in line with expectations. And also, one thing I like to call these is really umbrella measurements, because you're measuring everything underneath the umbrella of the zone of reactivity. So everything underneath the umbrella is what's important. It is what's being measured. And if you tune it for carbon monoxide and hydrogen, you'll get a measurement between carbon monoxide and hydrogen. If you're measuring a hydrocarbon or percent level hydrocarbon with methane, you'd also want to calibrate with some amount of hydrogen so that you can measure hydrogen at percent level as well with the methane measurement. So everything underneath that umbrella of calibration ensures that you have the right zone of reactivity. And then one other thing to mention is that we have different versions depending on the amount of the uses of these. All of our hot wire detectors, our hot wire detector can be used for combustibles, can also be used for methane measurement, and also can be used for high sulfur cases. That's not exactly the case for the RTD detector. So there is a decision point for when to use a hot wire detector versus an RTD detector. Our RTD detector is more stable when it comes to cleaner flue gases, but in any case, both are very proven over the last 40 plus years of installations. And really, the last thing to point out is that these types of detectors are capable of ppm measurements and also percent level measurements. So monitoring for ppm levels of combustibles and also percent levels of hydrocarbons. So just one thing to point out is that these catalytic detectors can be more sensitive to hydrogen, but that's especially the case when you calibrate to hydrogen. So if you're using combustible measurement, we highly recommend using carbon monoxide and hydrogen in the calibration gas. If you're looking for a variable fuel and you're expecting to have unburnt hydrogen, we recommend calibrating with hydrogen and or methane. So that's something to think about, and that we've really seen a lot in the lab, and that we've seen a lot of lab in testing. So we're getting close to the end. I just want to kind of summarize it all for you. We've talked about a lot. As we think about combustion measurements moving forward, when we think about all of these things that we talked about with set points and with combustibles and with reactivity of hydrogen, what are those measurements to think about? What really comes down to, well, if you have a high hydrogen fuel that has some amount of hydrogen and some amount of hydrocarbons, we still recommend the excess oxygen to ensure that you have a safe set point for process operation, to make sure that you have the right amount of excess air at the burner. I showed you the graph about correlations. Those correlations are very real to ensuring that the right amount of excess oxygen in the flue gas pertains to the right amount of excess air at the burner. There's also the combustible measurement for safety and efficiency. We talked about combustibles breakthrough. Need to monitor for that, whether you have hydrogen and or carbon monoxide in the flue gas. Very important to monitor, and also the opportunity to optimize the combustion process. We take combustion optimization very seriously, and we want to make sure that the air-to-fuel ratio is effectively balanced and optimized. And then finally, when it comes down to the hydrocarbons measurement at percent levels, whether it's normal operation or startup, monitoring for fuel leaks, monitoring for tube leaks, depending on the compounds depending on what's in your tubes, but monitoring potential fuel leaks, and then also for safe light-off monitoring. So that's what to think about for high hydrogen fuels, to make sure that you have full visibility of the combustion process. When it comes to pure hydrogen, say you're firing on pure hydrogen, this is also very important to think about. Again, we're going to stress and recommend the use of excess oxygen as a measurement for safe combustion control, making sure that you have the right air-fuel ratio, the right set points of excess oxygen and excess air at the burner. For combustibles, making sure that they have low-level hydrogen monitoring. That's where a ppm combustibles measurement comes in, even for monitoring for hydrogen, and also to provide a secondary point for air-to-fuel ratio efficiency. Again, monitoring for combustion optimization, and also making sure there's no hydrogen that's certain missing the flame and missing the oxygen altogether. So monitoring for combustibles. And then finally, for percent level hydrogen for safety. So again, monitoring for safe operation, especially if you're going to use hydrogen as a fuel. Typically, they start with natural gas as the light off fuel. So monitoring for light off, but also monitoring for fuel leaks, for loss of flame from the burner standpoint. So these would be the flue gas measurements that we recommend and that we see as we work towards pure hydrogen as a fuel. So I know we covered a lot today. Some takeaways to think about as we pull it all together. The first thing, hydrogen fuels provide a great versatility for existing combustion processes, existing refiners, existing operations to reduce the CO2 footprint, especially if you have a lot of small dispersed point sources. So very important to think about when you have a lot of different emissions, or if you want to just convert to do a quick reduction, even adding hydrogen to your fuel to reduce the amount of emissions created. So important to think about there. There's also the fact that from physically, hydrogen is lighter, it's faster diffusing, it's more flammable compared to methane. So recognizing that has implications, especially on the risk side, when it comes to using hydrogen as a fuel. Also on the combustion side, hydrogen flames are 10 times faster, they burn hotter, and they really vary depending on the heating values that you're looking at it on a mass flow basis versus a volumetric basis. There's also hydrogen fuels as a risk of flashback, which I can't emphasize enough because you want to be really mindful of that when it comes to premix burners or wide swings in composition. So if you're going from uh, from hydrogen as a fuel back to methane, be mindful of that, or from methane to hydrogen, be mindful of the risk of flashback and also the implications of higher NOx levels on the system. Other things we talked about, really flue gas analysis continues to continues to play three important roles in any combustion process: the role of the operational air-to-fuel set points, the role of optimization, and also the role of safety. We talked a lot about how those measurements are important and how they really play into the decision of what measurements you use in the flue gas analyzer. And then finally, we talked about, from a flue gas analyzer's perspective, we also talked about the umbrella measurement of combustibles and how catalytic detectors create these umbrella readings that are not specific to any species, but really to a zone of reactivity. Combustibles detectors offer percent level, a ppm level measurement. A hydrocarbon measurement, methane detector or hydrocarbon detector can really detect percent levels. And both are used, again, like I said, to ensure high hydrogen fuels are used in safe operation. So we covered a lot today. I appreciate your attention. I'll open it to any questions that we might have, so feel free to put them in the chat. I'll wait a couple moments to see if there's any online. Okay. So there is one question about calibrating a combustible detector to make sure that it responds to the process. The combustible measurement is very important when it comes to monitoring for combustible breakthrough. One thing I would say to this is to reach out to, if you are having issues with the combustible measurement, I would recommend reaching out to your distributor and or to our service team and or to myself, just to understand your case a little bit better, but also to make sure that that the electronics are the correct version, to make sure that the detector is right for the process. So it's all very case by case basis, but good question when it comes to calibrating a combustible detector. Any other questions? Okay, with that, feel free to reach out to me. This is actually my cell phone, so feel free to reach out to me via my cell phone if you have any immediate questions. With that, I really appreciate your time today. Thank you so much for sharing in this webinar today. I hope it's a good refresher for some of you. I hope it's good information if it's new to you. And I hope that we can continue to work together as we decarbonize the future of combustion processes and make for a cleaner world. So I'll hang on if there's any other questions, but thanks so much for your time.